Hi everyone, welcome back. So this is another data analysis video, and in the last couple of videos I recorded, I started talking about regression analysis. I created a video that looked at tests of assumptions for regression models and diagnostics, and then in the last video I conducted a simple linear regression analysis using both stats models and the Penguin software libraries. So what I'm going to do in this particular video to develop intuition for linear regression is I'm going to run a regression analysis to obtain the regression coefficients by coding the equations manually. So it's not entirely manual because I'm obviously using the pandas and NumPy software libraries and the kind of vectorized calculations that are possible using software like that. So I'm not kind of deriving the line or anything like that in order to obtain the slope of the regression line. But I'll kind of demonstrate how to use variance and covariance to obtain the slope of the regression line and the intercept and stuff like that. So just as a quick recap, linear regression, where we have one scale independent variable and one scale dependent variable, is most commonly calculated using the least squares method. What this means is the regression line is positioned in the place where it minimizes the squared distances between the line, which represents the predicted kind of dv values or values for whatever variables shown on the y-axis, and the actual data point. So it minimizes the distance between the line and the data points. Because all data is inherently noisy, there's going to be some variability between individuals in their scores on both whatever your independent variable is and whatever your dependent variable is. So we see that most clearly when we kind of use plots such as scatter plots to visualize our data. And the purpose of the regression line is to try provide us, using a straight line essentially, to provide us with a useful model that captures the kind of general pattern that we see in our data set, or the trend that we see in the data essentially. So as such, where the line sits is it's situated so that the distance between it and every data point in our data set is as small as it can be, taking into account every data point. If we moved it slightly, it would increase kind of the distance from one point by reducing the distance to another point. Okay, so when we have a simple linear regression model with one independent variable and one dv, there is an analytic solution, so we can derive the slope of the line. There's an equation that we could use to calculate the slope of the line. When we have more independent variables in our model, so we're conducting multiple regression, I think it may be a little bit more complicated, and we may need to just use computational methods such as the kind of software that we use, like stats models or machine learning libraries, other machine learning libraries. So we may need to use computational methods to kind of repeatedly fit lines and use some sort of cost function to work out which of those lines has the smallest squared deviation from the data points, and is therefore the best kind of model for our data, so the best location to place the regression line as such. So what I'll do in the following cells is I'll kind of simulate some data that follows a normal distribution and has a very clear linear relationship, and then I'll show how to fit a kind of simple linear regression model using equations for the slope and the intercept. Okay, so to start off, I'm going to import some software libraries. I'm going to import pandas as PD, NumPy as NP, and matplotlib. We'll create a scatter plot, and that will allow us to visualize where our regression line sits in relation to our data. It's often useful. I mean, it's something that you can do usefully when you have a simple linear regression. You've only got one IV, one DV. You can kind of plot where the line is. If you've got multiple independent variables, it sort of then goes to 3 and 4 dimensions. It's kind of difficult to visualize. It becomes a kind of plane or a surface, and then who knows what it looks like after that. But anyway, so I've imported those libraries. I'm going to generate some random data. And I'm going to set a random seed at 0 so the data can be replicated by anyone else using this particular notebook. So X is going to be the name I'll give to our independent variable as is conventional. And I'm going to generate a vector of 100 values, 100 data points with a mean of 1.5 and a standard deviation of 2.5. Okay, so hopefully you can see that. So X is going to be 2.5, which is our standard deviation, times np.random.randn. I'm asking for 100 data points, and I'm using plus 1.5, which will kind of give us the location essentially of our mean. Okay, and res underneath is kind of an object containing values of the residuals, so the deviation of each data point from the regression line. And then y is our DV, so the actual scores on the DV essentially, and I'm basically using our x variable and this kind of res object that I've created, which is essentially the residuals, and I'm kind of using that to calculate. I'm kind of adding a bit. I'm adding kind of a little bit of noise essentially, and creating the same sort of thing, an array or a vector of y values that relate to each x value. Okay, so let me run that. Okay. Next thing I'm going to do is create a pandas data frame to store these x and y variables. So as you'll be able to see in a second when I run this cell, it obviously creates a data frame showing, oh gosh, change that because I saw it, randomly generated data. So each of the data points is a floating point number, so it's a decimal number, and I'm going to create this using you've seen me do this before if you've watched any of my previous videos. Create a data frame object called df, and I'm going to use pandas. I'm using pd.dataframe method, and I'm basically just passing a dictionary, which is the part contained within these curly braces, and I'm passing it key value pairs. So I'm saying the key is this string x, so that's the label for x, and the value that's assigned to that is our object x, which remember is a vector of 100 values, 100 data points. And then y is also a string key, and the values passed to that are kind of this vector of 100 y values that we created as well. Okay, so if we call the header, you'll see what that looks like. Here's the first 5 rows. So we've got x and y. X is going to be our IV, and y is going to be our DV. So now that we have a data set to analyze, what I'll do is I'll calculate the various statistics we need to fit the regression line. So linear regression fits the line using the equation for a straight line. So that's y equals mx plus b. Where y is the dv, the dependent variable score, m is the slope of the line, x is the independent variable score, and b is the intercept. That's the point the line crosses the y-axis when x is 0. Or another way to think of it is if our value of x is 0, it's kind of be the average on our y-axis on our dv essentially. So this equation here, y equals mx plus b, is written in what's known as slope-intercept form, and when used for least squares regression, it's often rewritten to be in this formula that you're seeing here. So y equals alpha plus beta x. Okay, so in this form, the terms are simply rearranged, and different letters are being used for the slope, and different Greek characters in this case for the slope and intercept. So y is still the dv score, beta is the slope of the line, x is still whatever the score is on our independent variable, and alpha is now the intercept, what previously was beta. Sometimes you'll see this with plus epsilon added on the end, and that's kind of just some little error term to sort of highlight the fact that this is kind of never a perfect relationship, essentially. So to fit a linear model for our data using this equation, we need to calculate mean scores for our variables as well as alpha and beta, using all the data in our vector of scores for each variable. Okay, so first of all, what I'll do is calculate the mean for our IV for the x variable and for the dv, and I'm just going to use NumPy to do that. So I'm going to get x underscore mean. I'm creating two new objects. One's for the mean of x, one's for the mean of y. Just saving those values, and then I'm using np.mean, the NumPy mean method, and I'm passing x into one and y into the other. If we run that, that has created that. And if I kind of run the cells below it will just kind of print out what those values are. So what we can see here is that our independent variable x has a mean of 1.65, and this is close to the mean specified when we randomly generated the data. So I wanted it, if you remember up here, I asked for the mean to be 1.5. It's not exactly that, and that's obviously because this is randomly generated numbers, and you're going to get some noise in there, which is good as well. It's useful. It's it makes it more realistic. And the dv, the mean for the dv for the y variable is 2.74, as you can see there. Okay, so there are a couple of terms that we need for the numerator and denominator when calculating the slope of the line. Yeah, and these are the variance for the independent variable and the covariance of the independent variable and the dependent variable. Okay, so I'm going to create a couple of new objects. I'm actually going to create a couple of new features or variables, essentially. So firstly, I'm going to work out the covariance of x and y. So we've got our x variable, our y variable, and we want to know what the covariance of the two is. So I'm going to append the new variable called xy_cov, so xy covariance, to the data frame. And to calculate that, this is the calculation for the covariance. Essentially, I'm going to take the x variable and subtract the mean, the mean x score from each value in our x variable. So each of the data points that we have in our vector of 100 for x, we're going to subtract 1.65 from it, roughly. And then we're going to multiply that by pretty much the same calculation, but using the y variable, our dv. So we're going to take the y variable vector, and from each score we're going to subtract the mean value of y. So we're going to subtract 2.74 from each one. Okay, and obviously we're multiplying the x minus x mean times y minus y mean. We're multiplying those together, and that gives us the covariance of x and y. Okay, so the other thing we need is the variance for the independent variable, which is x. So to calculate that, I'm going to create another object called xvar, x variance, and I'm going to append that to the data frame. And that's to calculate that. I'm going to take each value in of x in our x variable, subtract the mean from it, and then square it, essentially. So we're working out what's effectively the sum of squares. Okay, so let me run that cell. And then what we can do next is calculate alpha. If you remember, that's our intercept, and beta, which is our slope. So we'll then know where the intercept sits for this data set. We'll know what the slope of the line is for the data set. So to work out beta, the slope of the line, what we do here is I'm going to take our xy covariance variable and sum the values and then going to divide by the sum of the variance of the independent variable, essentially. So hopefully you can see that. So I'm creating this new object called beta, which gives us the value of the slope of our line, or tells us what the slope is. And I'm taking the xy covariance variable using this dot sum method, and then I'm dividing by the variance of the independent variable, the x variance variable, and using the dot sum method on that as well. And then underneath, I've calculated beta first because we need that to work out alpha. So underneath we've got alpha, which is our intercept. And to work that out, we're going to take the mean score on the y variable, the mean dv score, and subtract that from that, the slope of the line times the mean IV score, so the mean score on the x variable. Let us run those two. So note, let me just read these notes I've put underneath. They may be useful. So note above that the slope of the line is calculated using the covariance of x and y and the variance of x. The covariance is divided by the variance. Okay, so beta equals covariance of x, y divided by variance of x. Also note that the intercept is calculated by subtracting the slope multiplied by the mean independent variable score from the mean dv score. Okay, so hopefully that's clear there. Let's print out these values then, now that we've got them. So let's print out the value for the intercept alpha and the slope for our regression line for this data set, and I'm going to just use some print function, use the print function, and use some f statements. And if I run that, you'll see we've got a alpha value or intercept value of about 2.25 if we round that to 2 decimal places, and our slope beta is 0.30 if we round that up. So if we kind of round to 2 places, this will round up to 0.30. Okay, right. So now we've got those values, we can make predictions for any given input value on the independent variable. So the regression equation for our model with these two values used to replace alpha and beta is y is equal to 2.25 plus 0.30 times x. So you take a value of x and you plug it into this equation and work that out, and it'll tell you what the predicted value on the dv is. So another way to say that is dv score is 2.25 plus 0.30 times whatever the score is on the IV. So we can obtain a vector of predicted dv scores for each value of our independent variable using the syntax in this cell below. So what I'm going to do is calculate the predicted y value or the dv score for each value in our vector of IV scores, our x, our kind of vector called x, essentially. And this will return an array of like 100 predicted values. So in order to do that, all I'm going to do is I'm going to create this object called pred_y, predicted y, and I'm going to use alpha plus beta times x. Okay, so this is kind of, and it's going to return this value, this kind of list of predicted values for all the x input values in our vector, our array. So there's a lot of kind of nice numerical computation going on here, which I'm not doing it all manually. Essentially, it's kind of Python is doing all these things for me. Not having to do these one at a time and then try to print them out. Yeah. So it'd be useful to visualize the data and the regression lines, sort of showing the predicted DV scores. A scatter plot will help us to better understand the relationship between our data and the fitted regression line. Okay, so what that is essentially going to do is predicted y is essentially showing us, if we put a line through those points, it's sort of telling us what the it's telling us, if we put around through the x values and their corresponding predicted y values, it's showing us where the line sits essentially. So let's plot regression against the actual data. So I'm going to use matplotlib. I'm going to create a figure. I'm going to use the dot plot function, which is just going to plot the regression line, and I'm also going to plot x and y using kind of red data points. So I'm going to create a scatter plot, and then I'm creating a scatter plot of our x and y actual data using kind of red data points. And the one above it here, I'm creating the regression line. Like I said, we're going to use that pred y and plot it against each value of x and plot a line through it. Okay, so let's run that and see what that looks like. You can see, I mean, because we simulated this data, it's not that noisy. It's actually a very neat and linear relationship there going. But you can see there so the scatter points are our actual data that we simulated, and the blue line is our regression line, which was which was useful, was easy to fit by sort of using this pred y object that we created. So what you can see above is we've simulated data that's highly positively correlated, and the regression line is kind of a good model to capture the pattern of that data. That would be a very good model for this data. It's linear, it's increasing as you go up the scores on the x value, scores on yr, and that kind of line gives you, if you were to just draw a line to say, well, what's the pattern of the data, the trend in the data, that's a really good model for it. Okay, so let me finish off. So just kind of summarize, so we can calculate the coefficients for a simple linear regression model using kind of analytic solution formulas like this. We have a bit of help here for doing all the kind of vectorized calculations that we need using libraries such as NumPy and pandas and things like that. I'm not having to do if you were to derive kind of the analytic solution for the slope of a regression line, it involves taking partial derivatives and stuff like that, and I'm not having to do any of that sort of stuff here. Yeah, it's all being computationally dealt with by Python for me in the background. We're using the formulas we used here, the covariance, the variance, things like that from our data set, the mean of x, the mean of y. We can calculate the intercept and slope for the least squares regression line that minimizes the squared distance between actual and predicted scores on the DV. And then we can use that information to predict scores on the DV for IV values that are not in our data set. So a useful thing about a model like this is, if we wanted to predict, well, what would we think if we had a value, say, of -4? We don't have a value there, but if we did, we could kind of work out what the predictive value of the dependent variable is based on our model. Okay. And plotting, as you can see there, plotting the data in the regression line gives us this nice visual impression of how well our linear model fits the data. When you just have one IV, one DV, that's kind of really easy to do and useful. Gets more tricky when you're doing multiple regression. Okay, so that's it. That is kind of linear regression on a made-up data set, fitted kind of manually using formulas rather than me getting Penguin or stats models to do all the work for me. Okay, I hope this was helpful and developed intuition around regression models. Thank you for listening.